Good morning guys, and welcome to today's worked exam answer video. Today I'm having a look at an AQA A-level thermodynamics question involving the Gibbs Free Energy equation and knowledge of entropy. So sort of what entropy is, why we have different standard absolute entropy values for different substances, and then we're going to do a calculation to try and figure out the minimum temperature at which this particular reaction is feasible. And there's quite a lot of marks for that question in particular because we are going to have to work out the value for delta H as well as the value for delta S, and then we're going to need to rearrange our Gibbs free energy equation, sub those numbers in to get that minimum temperature in Kelvin. So in terms of this question, we're thinking about the reaction of aluminium oxide and carbon, and then we've got this table of data here. And this table contains the standard enthalpy of formation data. That's what that tiny little F in there is referring to. So these are the amount of energies released when a mole of these two compounds are formed. We don't have any values for elements because standard enthalpy of formation, definition wise, is the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states. These are already elements, they're not compounds, so we don't have enthalpy of formation values. And in terms of this question, for those of you who may be thinking, oh, maybe this doesn't apply to me if I'm only in year 12, the standard enthalpy of formation data and the cycle that I'll be doing down here to work out the value for delta H is very relevant to you, because that's something that you'll be asked to do in the energetics topic. So that side of things, if you're a year 12 student, perhaps stick around and have a watch, fast forward obviously as appropriate, but certainly for year 13 students, obviously all of this is relevant for you. Also in this table we've got the absolute entropy values for each of the different substances, and you can see that the magnitude of these values is very different for the three solids compared to the gas, and that's something we're going to have a think about in the first part of this question. Something that I just want to draw your attention to before we get started on the questions is that we have been given the units for delta H and the entropy values in the table, and they will always do that. And there's two reasons why I'm pointing this out. One, because these are per mole, so that is the energy released when 1 mole of aluminium oxide is made, and this is the energy for 1 mole of Al2O3 in terms of entropy. The second thing I'm pointing this out for is the units for entropy are different from the units for enthalpy. So enthalpy and Gibbs free energy is in kilojoules per mole, whereas entropy is in joules per Kelvin per mole. So when it comes to our Gibbs free energy rearrangement and calculations down the bottom here, we're going to need to remember that, or certainly be able to look in the table and realise, okay, we've got joules and we've got kilojoules. Obviously we're going to need to get all of those quantities in the same unit, so we're going to go for kilojoules per mole. So whatever we calculate delta S to be, we're going to have to change that from joules into kilojoules, and that is something that students often forget when it comes to the calculations. So in terms of part A, explain why the standard entropy value for carbon dioxide is greater than that for carbon. So carbon dioxide has a value of 214, whereas carbon has a value of 6. And in terms of the state symbols, carbon dioxide being a gas, carbon being a solid, when we're thinking about entropy values, we're thinking about the disorder of the system. And when we're thinking how that relates to states of matter, the particles in carbon, when it's a solid, they're going to be in their neat rows and columns, tightly packed together in a very regular arrangement with no movement at all other than the vibrations of those particles sort of on the spot. So there's not a lot of disorder in that system. It's very ordered by comparison, so this value is very small. When we're thinking about carbon dioxide, on the other hand, as a gas particles, they're not in a regular arrangement. The particles have lots of energy, meaning that they have a lot of freedom for their movement. So by comparison, that's going to be very disordered and not very ordered. So we have to explain. So it's going to be because the carbon dioxide, being a gas, is more disordered than carbon, with that being a solid. And it's only 1 mark, so we shouldn't have to explain any further than that. But of course, we could go on to say what I have just done in terms of the particles and their arrangements and their movements in carbon dioxide and carbon. But all I think I need to say here for my 1 mark is carbon dioxide being a gas is more disordered than carbon, being a solid, which is much more ordered. So thinking of this idea that the more disordered the system, the greater the absolute entropy value will be for that substance. And we can think about that in terms of one particular substance in the solid, liquid and gas phase, and water is a really good example of that. So water, when it's ice as a solid, again, more ordered, so the value for water as a solid is a lot smaller than the value for water as a liquid, which is greater because the particles in the liquid have a greater freedom of movement to slide past each other. But then there's a massive jump between water as a liquid and water as water vapour as a gas, and that value is a lot bigger than the value for water as a liquid because of that increase in disorder that we get when the particles are completely free to move. Okay. Then we also need to be aware that when we're thinking about standard entropy values, they're all a comparison to the entropy value that we would have at absolute 0 Kelvin. So the next question is saying state the temperature at which the standard entropy of aluminium is 0 joules per Kelvin per mole. And if a substance has 0 disorder, it will have an absolute entropy value of 0, and at absolute 0 temperature, what we are thinking about is that that solid is completely crystalline. There is no vibration of any particles at that point. The particles are just completely still and as regularly and tightly packed and arranged as possible. So the value for aluminium being 28 shows that we have got more disorder at this particular temperature than we do at absolute 0. Carbon is only slightly more disordered than it would be at absolute 0. Aluminium oxide slightly more, and when we're thinking about solids and the comparison between these, MR comes into play. Not that that's relevant for this question, but yeah, everything is compared to absolute 0 Kelvin, which is where we say there is no disorder at all. Okay. In terms of the equation that we're going to need for the next part of our question, we need to make sure that we have memorised the Gibbs Free Energy equation. So delta G, which is the Gibbs Free Energy, is equal to delta H, which is enthalpy, minus temperature times by the entropy change, so take away T delta S. Now, it doesn't actually hint to you in the question that that's what we need to do. It just says use the equation and the data in the table above to calculate the minimum temperature at which this reaction becomes feasible. And feasible is the buzzword here. When we're thinking about feasibility of a reaction, the first thing I would want you to be thinking about is delta G. And when we're thinking about feasibility, we can't just rely on delta H, which if you're in year 12, you're probably kind of thinking at this point, which is absolutely fine, that whether a reaction is exo or endothermic determines whether it's feasible. And that's sadly not the case. And when you get into year 13, you will discover this concept of entropy, which is also very important. And so the Gibbs Free Energy equation is the balance between how important enthalpy is, how important entropy is, and then also brings in this idea of temperature as well, which is also important. So feasible, this is the equation I want you to be thinking about. We are wanting to calculate T, so we're going to need to rearrange this. How are we going to rearrange this when we don't know T and we don't know delta G? Well, this is where we need to appreciate that the first point at which the reaction is feasible, delta G will be 0. To be feasible, delta G would need to be less than or equal to 0. So we are going to set delta G equal to 0 because that's the first value at which the reaction would be feasible. Then we can rearrange this because we can say 0 is equal to delta H minus T delta S. And then I am going to take the T delta S over to the left hand side to get rid of this nasty negative that nobody likes. So T delta S is equal to delta H. And then if we want temperature, temperature will be equal to delta H over delta S. So we now need to work out what delta H is, what delta S is, and then we're just going to be subbing those numbers into there. I know, sounds simple. Apologies if I'm making it sound too simple, that's not my intention. In terms of how we do delta H and delta S, delta H, this is where the year 12 Hess's law standard enthalpy of formation cycle comes in. For delta S, it's perhaps a little bit more straightforward. We are going to do the sum of the entropy of the products minus the sum of the entropy of the reactants. Again, just thinking about the per mole part of this table. So I'll start with delta H. And in order to work out the value for delta H, we're going to need to use the equation at the top to make a little cycle. I'm going to drop my state symbols just to make life a little bit easier. Now, we've been given enthalpy of formation data, and it's always the data that drives the cycle that we draw. So we have formation data, standard enthalpy of formation of these compounds from their constituent elements in their standard states. So we're going to need aluminium, which in its standard state is a solid. We're going to need oxygen, which in its standard state is a diatomic gas, and carbon, which in its standard state is a solid. And then we should technically balance these elements at the bottom from either the reactant side or the product side. So we're going to need 4 aluminiums, we're going to need 6 oxygens, so 3 O2, and then we're going to need 3 C. Now, we don't need to do the arrows with the zeros on for the aluminium and the carbon, but if you want to draw those arrows and label them 0, you'd be more than okay to do so. What we do need to do is have an arrow pointing up to the Al2O3 because we're forming that compound, and an arrow up to the CO2 because we are forming that compound. Now, those values from the table, we've got -394 for the CO2, that would be for the formation of 1 mole, and we've got 3 moles being formed. So we're going to times that value by 3 because of this. And then for the Al2O3, again, we've got the value in the table for the formation of 1 mole, so -1669. We're forming 2 moles, so we're going to need to times that by 2. And how does this help us? Well, we don't have the enthalpy change for this reaction, but we can use Hess's law to go via an alternative reaction pathway, because the key thing is we're starting and ending with our initial reactants and our final products in the same states. So the enthalpy change is independent of the route taken. So I can now go from my reactants down to my intermediate, and then from my intermediate up there like that. And whenever my blue highlighter Hess's law arrows go in the opposite direction to the arrows we drew on initially, we need to flip the sign. So that means that my value for delta H will be equal to positive 1669 times 2, because the blue arrow for my Hess's law cycle here is going in the opposite direction to the black arrow that I drew. And then we always add all the stages in our alternative pathway. So we're then going to add that to minus 394 times 3. And that should give me a value of 2,156 kilojoules per mole. Apologies, I just needed to try and calm my cat down a little bit. You probably heard him meowing in the background, and he's still going. Apologies for that. So that's how we're going to get our value for delta H. And if you are an AS student, current year 12, that's the bit that you need to be able to do for your own potential end of year exams or AS exams that are coming up. If you are in year 13, approaching your A-level exams, then we also need to be able to calculate a value for delta S. So this is where we're going to do the sum of the entropy of the products minus the sum of the entropy for the reactants. So again, looking at the values in the table, that's for 1 mole. So in terms of our products, we have got 4 lots of aluminium. So we're going to need to do 4 times 28. And then we're going to need to add to that the 3 lots for the CO2. So plus 3 times 214, and that will be the value for our products. And then we need to do the same for our reactants. So we've got 2 lots of the Al2O3, so 2 lots of 51, and we've got 3 lots of carbon, so 3 lots of 6. That will give us our value for delta S, which is going to be 634. Just wanted to check I had that right. And that will come out, as per the units in the table, as 634 joules per Kelvin per mole. Now, if that's the only thing you need to calculate in your question, you would leave it in joules per Kelvin per mole. But because we're going to need to substitute that into our rearranged Gibbs Free Energy equation, and the units for delta H in kilojoules per mole and the units for delta G in kilojoules per mole, we're going to need to change it into kilojoules per Kelvin per mole. So when I know that the value I've calculated for delta S is going to be used in a Gibbs Free Energy equation, I will immediately convert it, because otherwise I would hope I wouldn't forget, but it's certainly good practice, and it just ensures that I'm always doing it that way. I'm teaching others to do it that way, and then hopefully you as students won't forget to do it either. So that will give us, if we divide the joules by 1,000 to get it into kilojoules, 0.634 kilojoules per Kelvin per mole. Okay. On the final straight now, so we've already rearranged our equations, so therefore temperature is going to be equal to 2,156 kilojoules per mole for delta H, divided by the 0.634 for my entropy change in kilojoules per Kelvin per mole, and that is going to give me an answer of 3,486 401 Kelvin. So that is the minimum temperature at which this reaction will be feasible. Now, if we just have a think very quickly about the magnitude of these values and what they show, delta H here being very positive suggests that this is a highly endothermic reaction. And the value that we got here of 634 joules per Kelvin per mole shows that there's quite a big jump in disorder. There's an increase in the disorder of the system, which is a good thing in terms of what we're looking for in a reaction. It's entropically favourable. So endothermic reactions, not so great, but where there's an increase in disorder, that is good. So when we then think about our Gibbs free energy equation, delta G equals delta H minus T delta S. Delta H is quite large and positive, so in order to get delta G to be 0 or a negative value, we're going to need the T delta S to be very big, because we're going to have it bigger than 2156, which is why this temperature is quite high, and that's the minimum temperature to get delta G to be 0. If we made this higher than 3401, then we would get delta G to be negative, but we were asked for minimum temperature, which is always what you're going to get when you rearrange it like this for this kind of scenario. One more thing finally, in terms of this delta S value being positive, a nice way to check whether that is what you were expecting is to have a look at the state symbols. So we've already kind of talked about, you know, aluminium oxide, carbon and aluminium all being solids and the CO2 being a gas. In reactions where we go from solids and we make gases, we're going to see a big increase in disorder. So before I even did that calculation, I knew not only that I was expecting it to be positive, but I was expecting it to be significantly positive, because there's quite a jump in entropy. We've got 3 moles of a gas being made, whereas we started with 5 moles of a solid. So yeah, I was expecting a big increase in disorder and I got one. So that's a nice little check we can do. And there we have it. So quite a lot in that question, which is one of the reasons why I chose it. Hopefully everything I've said makes sense. I apologise for my meowing cat once again, and if anyone has any questions that they want to ask me, please do not hesitate to do so, and hopefully I'll be back with another video soon. Thanks so much for watching, guys. Hope you all have a lovely day.